All right, let's talk about cool little objects. And what is an object? Well, there's two pieces to it. There's a definition, which is the things that go into it. That is the functions that are associated with it, which we call methods. And all a method is a function with an extra parameter. And there's some historical reason why it's called a method. But in any case, it's a function with an extra parameter. And it has a guaranteed initialization. In some languages like C++, there's also guaranteed deinitialization. But by and large, the thing that makes it a class is going to be this special stuff called inheritance, which we're going to get to in a minute. But classes are a good but not perfect way to organize your code. And the book just says how wonderful they are. Well, I'm going to point out to you the wonderful part, and I'm also going to give you at least an example of where it doesn't work, so that as you're using them, you can say, is this what I want to build and how I want to build it? It gives you a little bit better perspective on them. But what we're going to do is we're going to model a vehicle. And there are similar kinds of classes in the book in the chapter. They talk about animals. They talk about cars. And we're going to take a look at that and see how we go about modeling that. And basically, at some level, a class is an association between data and the operations that we're going to do on that data. And this is one of the design methods that you can use to build large programs. It's not the only one, but it's a really good one. So I use classes. I don't exclusively use classes, but I use them and I appreciate their strengths. And there are a lot of strengths. Now, Python, this is one of two things that we really have to build chunks of code of significant size. The other is a thing called modules, which has to do with basically taking a class and putting it in a separate file so that you can use it. And you've already seen the use of this. We have imported a module that deals with comma-separated values in files. And when you look at the classes, suddenly you ought to be saying, oh, yeah, this CSV thing that we imported, yeah, those functions that I called in association with it, those were methods on the class. Those were functions with an extra parameter. And this extra parameter goes in front. So there's a bunch of words you have to use. Like most things when you're learning something, there's terms. The first one is class. And class is a reserved word like if or def in Python. And class is the word that we use to define that this set of functions all works together on this set of data. And there is a special constructor called __init. And I will highlight that does the initialization. And whenever you create a class, this is what gets called. And you have to pass it some parameters, at least self. We'll tell you what self is in a minute. But this is how you set up the data inside the class to start off with. The reason for this special init function is that when people didn't have classes, one of the most common errors that they would have is not properly initializing pieces of data. So when they built classes, they included that. It's generally called not init, but a constructor. And in fact, as far as I know, every object-oriented programming language, which means it has classes, has some sort of automatic initialization that you can use. There is another thing that we're going to get to, which is how you do a main program. I'm not going to cover that in this lecture. That'll be in the next lecture, but it has to do with using another one of these things called __main__. And that is a good way of separating out your test code from your classes so that you can build them together, but you can have a means by which of testing and not contaminating your class with your tests, but still have it there as a part of the code. And we'll show you that. Now, whenever we have a set of data, we have to have some way to refer to the set of data that is shared between the methods in the class. And in Python, that is called self. In some other languages, it's called this. But whichever one you want to call it, this is how you get to the data that is associated with your little object. Is you say self dot some value. And if you look right here, we have self.year equals year. So self.year refers to the data in the class. Year here refers to this year up here, the parameter to initialize it. So when I create a vehicle, I'm going to save off the year that it was built. Now, what you're going to see here is that there is the definition of a class, which is, this is the definition. This is how it works and what data it stores. That's all of that. But later, we're going to want to actually associate real values with it. Like I can say self.year equals year. Now, that doesn't tell me what year it was born in. That says how I'm going to handle years. This is the implementation. This is how it looks and what values it stores. As opposed to saying, I want one of these vehicles. And you know that the most common car manufacturer in the world is Tonka. And consequently, we better have a Tonka truck built in 2020. Because, if you're going to buy a truck, you want to get, the leading world manufacturer of trucks, Tonka. So this piece down here, when we actually associate real data with it, that is an instance of the class. And instance is one of those words. So what classes do is they have, here's how I'm laid out. Here's my behaviors. And then when you want to use one, you say, okay, I want this class and I want to associate its set of behaviors with some data. Remember that classes, what they are, is an association of code and data together. We create a definition for a class, how it works. When we actually do a real class, now this is an example, what we're going to want to do is we're going to want to take that class and we're going to want to test it because it has implementation. And at the point at which we test it, we're going to give it some data and we're going to run things in it and see if we get the right results. Just like a function. But the difference is that a class maintains this information from call to call because it has this underlying parameter. Now, what I did down here at the very bottom of this example is I just printed it out. And you're going to get an undesirable result when you print it out. Let's actually go run it once and see this happen. So if we do Python, okay, and I run it, and it prints out this icky thing down here that says, oh, wow. Inside main, remember I said underscore underscore main? That's showing up as a piece of information suddenly. We have a vehicle object because a class is an object, and it has an address, and that's all it tells you is where it stored it in memory. And that is not really very informative to us human beings. It's an undesirable result. Not wrong, just it didn't meet the criteria of printing out anything useful for my class. Now, one of those things that you can make that is useful to actually give the class its first useful behavior. I mean, we have a behavior in here we haven't used yet, set mileage. We'll get to that. But here is our first useful behavior, is you can do underscore underscore stir underscore underscore and pass itself. And stir converts the class from whatever its internals is back into a string and returns it so that you can print it out. And here's where some of the magic and the power of classes comes in. Print has never seen a vehicle, but if you have this function in it, this method stir, inside the class, it'll say, oh, you have one of those in your object. Well, when I want to print it out, I'll just call that, get back the string, and I'll print it. So this allows you to extend the existing capabilities inside the language to make it more useful. And that's part of the magic of classes, is because they can have these standard interfaces that we deal with, that other things suddenly can start to use them, and you can extend existing software with new capabilities. So now when we print out print, okay, this is in version 2 of vehicle, I've added this function down here, this method called stir. And what it does is it does a F double quote string to format the string, and it prints out what the vehicle is, the year it was built in, and who the manufacturer were. So it takes some of the data inside here, and it converts that into information that's in a string. Now notice I left out odometer. It doesn't tell you what the mileage on the vehicle is yet, but this gives you a good start on being able to say, okay, whenever I print out one of these objects, here's how I want to see it as a human being. Here's what I do with its insides, and return this as a human readable piece of information. So let's go run that. That's vehicle 2. And this time we get something we can understand. We see that the instance V1 is a vehicle, it's a truck built in 2020 by Tonka, the world's leading truck manufacturer. And V2, we have another kind of vehicle, a moon rover built in 1969 by NASA. Clearly a used car in that they've parked someplace. So yes, we have 2 different kinds of vehicles here. Now, this is what we have for some simple vehicles and how we convert it. Okay, so let's kind of look at how we call this set mileage method, how we actually set the mileage. Now you'll notice that it does a check. You can't set the mileage to a negative value. It's just like the odometer, you can't take miles off of it. And at least you're not supposed to be able to in most vehicles. They're manufactured that way so you can't cheat and lie about how many miles there are in a vehicle if you go to sell it. And otherwise, it just takes whatever miles you're adding and it adds it to the odometer. Now, this isn't the only way to do an error and probably not the best, but it's a good example for this point. If I were to put in an error, I would use some error handling in my module so that it works with the error system in Python. We haven't covered that yet, so we're just going to print something out. But the important thing is it does handle an error and we can call it. So let's say that we take V2, the moon rover sitting out there on the moon right now, NASA's used car, and we say that it went 2 miles. So we're going to add 2 to it, and we're going to print it back out. Now you'll notice that I've actually changed the string format now to include the odometer reading, so we know the mileage. So when we run it, by golly, the first time we printed out V2 is a 1969 NASA with a mileage of 0. And the second time we run it, you'll notice that now it has a mileage of 2. Now, interestingly enough, we have this very odd thing that we don't have any mileage on our Tonka truck. And man, if I owned a Tonka truck, I'd be running it around the living room. So there you go. Okay? That is how you call a method. Now let's take a look at what we actually have in the code for that. Let's say down here we did v2.setMileage. Now remember, v2 is the set of data that's associated with the class, the instance of the class, and we do dot and the name of the method inside the class. And then we pass the parameters. So if we look at setMileage, here is the magical first parameter. That's the instance that we call self inside the class. Outside the class, it's called v2. But inside the class, it's called self. And when we do something to self, we say self.odometer. Remember, that's what we created up here, is self.odometer starting out at 0. So we do self.odometer and we do some computation on it. And in this case, we do addition of whatever these mileage are. So this second parameter that we passed v2 as the first parameter, that's self. The second parameter in this case is 2. Just like a regular function, except we've got this automatic first parameter that's required. And in this case, we pass that, it becomes n, and we use it to add to the odometer inside the class. Now, I've also added this other function here, getMileage, that allows me to extract the mileage outside the class. Inside the class, I can refer to the odometer by the name of the variable. Outside the class, I would have to get this value by calling getMileage and returning it. So this gives me protection. It gives me control over how the things are changed inside the class. For instance, there's no way to change the year that the class or that the vehicle is made. There's no function in here that changes year. Once it was created, that's the value it has. I also can't change the vehicle type. I can't change a Tonka truck into a moon rover. Nor can I change the manufacturer. Once those things were created in the class, up here in the initialization, they're basically fixed. For the entire run of the program. You can't change them. Now, that provides us with a lot of capabilities in terms of saying, these are the ways in which you can interface to this data. I'm going to put a walled garden around it, and I'm going to say, only through these doors can you come in here and change the data. I have protection on this set of state information. And whenever you use a class to maintain state, this is a really good thing. If you just have people arbitrarily changing data, you get unexpected results. Now, you can also do lots of things to validate that the data is right. For instance, it doesn't do this in set mileage, but maybe we want to say that, you can only add less than 1 million miles to a vehicle ever, because vehicles just don't last that long. Well, most of them don't. But, and most of the ones that don't last that long, you wish they would before they're done. But, it gives you control over how you change state information. And when classes are used in this fashion as containers for state, they're very, very effective, and they have lots of benefits. They are excellent state containers. Now, that doesn't mean that this is the only thing we do in programming, and that is one of the mysteries of programming languages, is languages like Java. Now, Java is not JavaScript, remember, but Java, where it says that everything is an object. And I'm not one of these everything is an anything person. I'm more like, here's the good stuff. Let's use the good stuff. Let's work around and let's ignore it and do other things when we get to the bad stuff. So I want to give you one more example of what we can do with vehicle. And this is how we build more complicated things with objects. And this is how we group them into a hierarchy. And the term that we use for that is inheritance. And there's good and bad things about inheritance, just like there are most things, but I'm going to change my vehicle. And this example is a little bit longer, but I think I've got all the code where you can see it here. I still have a vehicle. It still has set mileage and get mileage and stir. But I am going to do two things. First of all, I'm going to introduce airplanes as a kind of vehicle. So now I've said an airplane is a vehicle, but it has a different initialization function, and it has a different stir function that includes max speed and wingspan, because Tonka trucks don't have a wingspan. They have a width, but they don't have wings because they don't fly. Well, unless you talk to my kids, in which case every once in a while they were flying through the living room. Not necessarily a bad thing, sometimes for fun, It's good to take your Tonka truck and have it up above your head flying through the sky and taking trips to Mars and things like that. So if you're going to add some stuff to it, we still want to maintain the existing things in here because we built some code there that's useful. But this is a specialization, a derivation of vehicle into a specific kind of vehicle, a different kind of vehicle, or a vehicle with more capabilities. And when we do that, we use this thing called inheritance. Now, this right up here in the class specifies what kind of a critter it is. It says an airplane is a vehicle. And you notice I use the term is a, and that's quite often how it's referred to. But when we initialize it, we'd like to be able to call the initialization for vehicles, and the way we do that is with this function called super. Super returns the thing that we are deriving from, the base class. And at that point, we can say, yeah, I want to call the init function. That's this init up here. And I want to pass it these things, because it still has a manufacturer, a vehicle type, and a year. So I'm going to call it with those things, but I'm going to add some additional data down here. A wingspan and a max speed. So I've built on top of existing code and I've reused it. And that's one of the other tremendous advantages of objects, is the ability to take existing things and adapt them and modify them to be better things in our code. So we get to take an existing vehicle and we get to create an airplane. Now, as long as what you're doing has a hierarchy, and that's why they use things like animals and dogs and mammals to explain this. Or it's real nice here with vehicles. As long as it has a hierarchy, this is a really good thing. I mean, I can't stress enough how useful this can be. Okay? And when we talk about some of the limitations of objects, we're going to look at things that don't naturally fall into hierarchies, because not everything in the world is a hierarchy. Now, a lot of things can be fit into a hierarchy paradigm. And because most things can be stuffed into a hierarchy, okay, this becomes a good, as in like 80% of the time, this is the perfect way to do it. It's just that when you take some of those other 20% and you try to stick a square peg in a round hole, that square piece of software trying to fit into the O of an object size hole and pound it in doesn't work well. We'll get to some examples on that. Now, what did I do with stir? You'll notice something happened here. I have a string function inside my airplane, and I have a string function inside my vehicle. Now, what happens is, if you replace a function, you can say, yes, I still want to have this behavior called underscore underscore stir underscore underscore. And I want it to be able to interface to print. But whenever it's an airplane, instead of calling that other one, I want this different behavior. So not only can you add stuff to the capabilities, you can replace existing things in a vehicle, in a class, with new things. So what I probably should do is I probably should have built this as a base vehicle that didn't have an odometer, because remember, my Tonka truck doesn't have one. And then when I did trucks or cars, it has an odometer. But when I did toys, it doesn't. But I didn't do that. And here we're going to replace this stir with one that prints out max speed and wingspan. Some properties that are useful for airplanes. Now, I also did an auto vehicle. And the auto vehicle, again, inherits from vehicle. And it just has max speed. It doesn't have wingspan. So, this is a good thing. Now, here's where we're going to say, yes, but... Okay, and here's an example where that's real easy in the yes, but objects don't match to everything. What happens when we invent flying cars? And they have a wingspan, but only part of the time, and some of the time they have a max speed that's different than their other max speed, depending on whether or not they're flying or driving down the road. And that gives you your first clear example of, okay, objects work for lots of things because I can build a hierarchy, but what happens when it's not a hierarchy? That's one of those things that you have to think about in terms of your design of software, is does it make a good fit? And if not, what are you going to do about it? And there's obvious things that you could do about it in the code. I mean, you could have is flying as a property of vehicles, and you could create a special class of flying cars. That if it's flying, it has this speed. If it's not flying, it has this speed. If it's flying, it has a wingspan. If it's not flying and sitting on the ground, it doesn't have a wingspan. And so you can build around that. But when you do your design, you have to be planning ahead for, yeah, here are my good cases where everything fits, and here are my edge cases where I have to say, oh, but there are these other cases you got to deal with. And depending on how important those edge cases are, determines a lot of the effectiveness of your class. So let's run this fourth one and see how it goes. And I've actually done more output here. We have this kind of an airplane that has a jet engine, a Pilatus PC-12NC. And its max speed is 581 miles per hour, with a wingspan of 41 feet. And we have a Cherokee built in 1969 that has a max speed of 185 miles an hour with a wingspan of 32 feet. So we've added some airplanes to this. And we still have our Moon rover built in 1969 with 2 miles on it, sitting in the used car parking lot on the moon. So different kinds of properties can be added to things to make them work in different ways. And the things to take away with this is there's a whole bunch of vocabulary around objects. Inheritance means you're building a hierarchy. A class, what a instance is, that's when you have actually associated the data with a class to say, here is an instance of this class. That's an instance. How you get from a child class where you've inherited to the parent class, in the Python it's called super. How you set up and initialize the class when it gets started. That's the init functions. And how those work, and why we have init functions to prevent errors in our code, which is useful. The fact that classes are pretty good at reusing code. So you can say, I'm going to build some basic stuff and then I'm going to reuse it over and over in other things. The fact that classes can extend existing stuff so it becomes more useful. And collectively, this entire set of things with classes, inheritance, initialization is what we refer to as object-oriented programming. And object-oriented programming has become the dominant form of programming. It's not the only form. There are some really nice classes here at the university in functional programming. We've mentioned that as an effective way to test code, and there are some advantages to that. But if you go out in the world programming, you're going to see lots and lots of things built with objects. The primary reason, in my opinion at least, why this has come about that object-oriented code is the most common is when you sit down and use a computer, you're usually looking at a screen, whether that is, your iPhone or a Mac or a PC, and it has things like buttons on it. Like up here, I've got a red, a yellow, and a green button. And when I hover over those buttons, they have a behavior. In this case, the little green one pops up a menu. The little yellow one and the little red one don't. But if I hover over buttons, they have actions that are associated with them. And those different things, like clicking this button and bringing up the search page for Google, and this little area up here that has tabs, each one of those regions on the screen and how they interact with characters and how they interact with a mouse or with a touch screen like on your phone, what they do and how they interact makes a natural hierarchy of objects. And that natural hierarchy of objects turns out to be really hard to build because there are a lot of capabilities in a graphical user interface. But once you've built it, it becomes very reusable and easy to understand and code with. Now, if you go back to like 1999 and you look at coding and software, when most of these languages, and Java was created in 1992, so it's 7 years old at that point. Okay, it's past the toddler phase, and it's running pretty good. But you look at programming in that day and age, probably 90% of all the code being developed had to do with user interfaces and how we build the user interface, and only 10% of it had to do with the underlying work that a program did. And if 90% of your code can be built in a more efficient functionality with objects, then that's going to be the primary thing you're doing, is using and building with objects. So some of these other paradigms like functional programming or data-driven design or state machines, all of these other things that we might do really fell into the background. But 1999 was a big year because that's also the year that we started seeing applications built for on the web. And there's no particular reason why web applications need to do nearly as much stuff with objects, although lots of them still have a user interface. But there's some tremendous separation from what you see in the browser when you bring up some kind of application like GitHub. And this is a user interface with chunks on it, but it's specified as a document, not as an object. And this document model that we're using today for almost all new applications are built with this document model has things that aren't inherently objects in it. So, it is not a purely object-oriented world anymore. And consequently, there are programming languages that have gone away from objects to other things. And you see a lot of stuff being done with functional programming. In fact, there are some very important front-end packages that do functional programming. If you've ever heard of a package for building functional or front-end stuff called React, React is a set of objects for managing the user interface, but you also want to manage state, and quite often that's done with another package that works with React called Redux. And Redux is a functional programming system. So we have both objects and some other things. And consequently, although objects are a great way of organizing, they're not the only way, and they're certainly not something that is the one true way for all pieces of software. And one of the things that I like about Python is that although it has objects and they're useful and well put together, and I use them, it isn't the only thing in the language. And it doesn't box you into saying, by golly, everything is an object and we will only build objects. It says, objects are useful and we'll do a good implementation of objects, and we have other things in the language that you can use as well, so that when you run out of the capabilities of this great system of objects, you can do something else. And that combination makes for a language that is even more powerful and more useful. And the thing that you see in a lot of languages today, like you'll notice that I do a fair amount of programming in Go. Go is a language that has interfaces, and interfaces can implement objects, or they can be used to implement other things. And Python, it has objects, but it also has non-object-oriented programming. And you see a lot of languages like this, like Apple developed this language called Swift, and Swift has objects. It also has functional programming, so that you can get beyond just one way for everything and actually have a more useful language. So this is my first piece on object-oriented. We're going to have a second piece on object-oriented, where we're going to delve into a more complex example, because it is the dominant thing, and you are going to see a lot of stuff that uses objects. And that's done for some very good reasons. With that, I will catch you later.